composite bodies. You can write it as a composite body body consists of a series of connected, I would say, I can write the word connected there. Connected, I'll put in quotation, simpler shape bodies. Right? We'll talk about what we mean by simpler. Simpler is a relative kind of term, but what do you mean by simple? What is complicated? And where do you draw the line between simple and complicated? We usually have a table of properties, but what we're trying to say, well, let me give you a couple of, actually I have got some figures so I can show you what, at least in engineering term, what are we talking about? If you look at figure 7 there you go. It's a cross section of a beam. Like it's a cross section of an L-shaped beam. Right? We'll talk about these actually later on when we look into more kind of applications. Or it's just a piece of concrete, right? When you want to find, you want to find its center of, you'll do that, there you go. When you want to find the center of area or center of gravity for this, or center of mass. It's a composite area, meaning that if you look closely, I can probably divide this into simpler areas like this. Let's divide it into this, and then maybe this, and this. In this case, I can divide it into two, estimate that using two rectangles, depending on what does it look like, what things look like, right? So here I have two triangles here on the sides, relatively triangle. Maybe you have to do a little more cautious and subdivide it more. Then you have a rectangle there, other form of shapes, simple shapes there. Those shapes you might be able to even divide it into one, not what I meant, one triangle and rectangle. Same story here. So you can keep going until to make it, form this area or this body using simpler shapes. That's what we mean by a series of connected, simpler shaped bodies. All right. Now, so what? So if we can do that, then the center, let's say XC, like center of, did I use C when I was introducing this? I just use X bar. So let me just use X bar. I interchangeably use both of them. So X bar is basically sum of all those bodies, center of mass, center of volume, or center of area, depending on what you're calculating. So in this case, let's go with center of gravity, right? For center of gravity, for instance, that would be I from 1 to N, whatever number of bodies you can divide this body to, composite body to, xi wi divided by sum of wi being the weight of each body, and xi being the center of. So let me just be consistent. Xc, x bar. X bar being the centroid of that specific body, a center of gravity of that specific shape. Right. So in this case, if I know the center of gravity for this shape and volume for this shape, and I know the center of gravity for this shape, weight for this shape, and center of gravity for this shape, then I can just sum them up and divide the total weight. So in this case, this becomes x becomes summation of x1 w1, or let me not write it, x1 w1 plus x2 w2 divided by w1 plus w2. That will give you center of gravity for this composite body, x. Same thing you can do for y. YC for a composite body is basically whatever y each body has, right? Center of gravity for each body multiplied by the weight of each body, I from 1 to n, number of bodies you have, summation of weight of the bodies. And same story for Z. Center of area, center of gravity for each body multiplied by weight of the body, right? Sum them up, divided by summing of the weight for the bodies. That's for center of gravity. Center of gravity. Now, same story for center of volume, center of area, center of mass, whatever you want to calculate, right? If you want to calculate center of volume, for instance, right, that would be summation x bar I volume, so VI, over sum of all the volumes. YC for center of volume would be Y VI, I from 1 to n divided by sum of all the volumes from 1 to n. ZC would be a summation of Z I's VI, right, for each body. If you divide into simpler bodies, for each body where the Z is coordinate, center of Z coordinate for center of volume for that body, multiplied by the volume of the body divided by summation of all the volumes. Area, you get the same thing. Right? I'll just write the area as the last one, but for the line is also the same thing, right? It's just the same process. If you have a wire or line, it just becomes X I L I, length of that. So for area, this is center of volume for a composite body. For an area, you'll get XI, AI, I from 1 to n, summation of AIs, I from 1 to n. YC would be summation of YI, AI, divided by summation of AI, I from 1 to n, depending on how many simpler bodies we can divide this to. ZC is from 1 to n, ZI, AI divided by summation of areas, I from 1 to n, right? This would be the center of volume, or centroid of volume, or centroids of volume, right? Same story as I said for wire or for now, how do we use this? All right, that's the general idea. And remember, it's very important, we'll see in examples, that it's not just about areas you have there. You can have cutout. So for instance, if you can estimate an area, let's say I have an area like this, and there is a hole in the middle. This is the area I'm trying to find. Now, I can say this area is basically a rectangle minus, I don't know, minus a circle. In that case, in that summation, you have to put negative for that circle. We'll look at an example, a couple examples, we'll see how does this work. But it can be forming that body by adding multiple parts together, form a composite body, the body you have, or it can be adding few parts and subtracting few parts, as long as you know those components or simpler shaped areas, lines, or volumes, centroids. It's a general idea. Now, how do we know for those what simpler shapes, better to say, should we divide this composite area to? You're given a table. So for lines, for instance, right here, for lines slash wires slash slender bars. Let me bring the table here. I'll talk on that table. I think there's a table here. All right, so let me bring it here. Centroid 2. This is a table for simpler shapes, as we call them, right? The shapes that you know you have information about. If you're given a wire, you're given a composite body with, it could be even piping system, depending on how you look at the pipe. If the pipes are so thin, you might be able to assume that they are like bars, and you don't consider if the length of the bar is much, a pipe is much more than the diameter, then you might be able to estimate that as a line wire or a slender bar. So what does this table tell you? In this table, let's see how can we read this. We have the shape here. We have quarter circular arc. We have semicircular arc, and we have arc of a circle. Right? This is quarter. Right, if I can clean that up. This is the quarter circular arc. This is semicircular arc, and this is the arc of circle. Quarter circular arc, that area, if you look at them, this one just. This, what does this tell me? It tells me that for quarter circular arc, the centroid is placed at, if the radius is r, right, the radius of that quarter circle is part of the circle, right? If the radius is r, then the centroid is located at x bar here, x bar away from the vertical line, this line. What is that x bar? 2r over pi. The centroid, represented by C here, is also located at 2r over pi above the horizontal line. It's important with respect to where. Later on, you'll see we have to be careful, because you have to find the centroid of the composite body with respect to one coordinate system. So you have to make sure to add whatever is needed to convert that coordinates into the general coordinate system for the composite body. But just pay attention that x bar is the distance from this vertical line, y bar is the distance from horizontal line. Now, and the length of the arc is also given, right? Because you know, and that when it comes to bar, let me just write it here. This becomes xi li over summation of li. Li is being length of the bar. Yc becomes summation of yi li over summation of li, and zc becomes summation of zi li over summation of li. Right? These are like same equations I wrote here. This is just for a line, right? Or wire or slender ball. Right? So you need to know each components when it comes to a line. X bar, Y bar, and Z bar, and the length of that component. So in this table, you're given X bar, Y bar, and the length for the quarter circular arc. Same story for semicircular arc. X bar, well, if the origin is here, the X, the coordinate, the C, center of this semicircular arc, is located at exactly where the origin is. Pay attention where the origin is. Origin is here. Okay. And y bar is located as 2r over pi above the horizontal. And the length of the arc is pi r. So now I hope you understand what this table is telling us. Same story for arc of circle. Right? Let's say we have a random arc of a circle. I have a circle, just this random arc. As long as you put the coordinate, if this is your horizontal line, your center of line for this piece, these are simpler shapes. The origin of this, this centroid or the center of this arc is located at y bar 0, meaning that it's exactly on the horizontal line, and it's at r sine alpha over alpha on x, right? Distance from origin. If distance from origin is x, this distance, that distance is r sine alpha over alpha. R being the radius for this arc of circle, and then alpha would be, if you put the line exactly in the middle, the angle between the line and both sides of the arc. And you know also the length, 2 alpha r. Remember, alpha here should be in radians. I'm just going to put it here as alpha in radians.